for concentrations and for gases. So we have our Kp, or anything K is always products over reactants. And there is one thing that I need you to think about. There should never be any solids or liquids in your equilibrium expressions. So if I were you and I'm writing the Kp, I'll look at the state of matter for each reactant or product and notice whether it's a solid, liquid, or gas. If it has a solid, liquid, or gas, I'll just go ahead and cross those out. And then one thing that you should also remember is that your coefficients become your exponents. So to write the Kp, and since we're talking about gases, we have to put them in parentheses, products over reactants. We always have to put P to indicate partial pressure. If you do not do that, the AP College Board will mark you incorrect. And then your products are going to be written as subscripts. So it will be CO2. This will be H2O. And your reactants will be C3H8 and O2. Now remember, your coefficients become your exponents in the equilibrium expression. So your coefficient for CO2 is 3, and your coefficient for water is 4. For C3H8, it's 1, and then for O2, it's 5. So that is your Kp expression. For this Kc expression, we are going to do the same thing. Kc is equal to the concentration of your products over your reactants. Now, this, remember I told you if you notice there's a solid or liquid, go ahead and cross it out, which means that there will be no reactants under here. So our Kc expression will only involve our products. I'll just go ahead and put Ag plus, remember the charges. If you do not include the charges, since we're using ions here, you're not going to get it correct. The coefficients, since there are none visible in front of each product, we call those 1, or we could write them as 1. And so our Kc is equal to the concentration of Ag plus raised to the first power and the concentration of Cl minus raised to the first power. The difference between the Kp and the Kc, notice that with the Kc, we're talking about molar concentration and we use brackets. Those units are measured in M. And for Kc, we use parentheses and the units or partial pressure is usually in ATM. So again, for this Kc, we're writing Kc, so we're talking about moles or molar concentration. And I look at my states of matter and I notice that there is only one liquid. So I'll cross that out. And so my Kc is equal to products over reactants. Kc is therefore equal to the concentration of H3O plus raised to the first power and the concentration of C2H3O2 minus raised to the first power and over the concentration of HC2H3O2 raised to the first power. And that's your Kc. Again, your Kp, all the states of matter are gases. And so we have to be particular about writing the Kp. Kp is equal to parentheses. There's only one reactant. Remember, partial pressure goes first. And your products, they have to be written as subscripts. So it will be PCl3, Cl2, and PCl5. They're written as subscripts, and then the coefficient becomes your exponents, 1, 1, 1. And that's it. For the Kp here, first thing that you want to do is to identify where there is a solid, liquid, or gas, or aqueous. And since we see a presence of a solid, we cross those out. So our Kp will only involve one species, and it's the gas that we're talking about. So we're going to put that in parentheses and put partial pressure, CO2 as a subscript, and raised to the first power. And that's your equilibrium expression. When we talk about Q versus K, we're talking about the concentration of your reactants versus your products at equilibrium. So if we look at A, B, C, and D, we're given each reaction equation and we're given the KeQ. What we're noticing is that for the first example, KeQ is 2.2, and for the second one, we see that KQ is 1 times 10 to the minus 15, and for C, we see KQ equals to 6.3 times 10 to the 4th power, and for D, or KQ, is 110. It's really good to identify any patterns or any anomalies or anything that's an outcast. And this one is very small. And I know this because I'm looking at the exponent on the 1 times 10 to the minus 15. Whenever you notice that your KeQ is a very small number, it favors your reactants. And then whenever your KeQ is very large, as in this case, it favors your products. These two also favors products because our KeQ is greater than 1. One way that I like to visualize it is by making a number line and put 1 here. If my K is greater than 1, that means the reaction will favor products. What that means is that since our KeQ is equal to products over reactants, or products will increase and or reactants will decrease. So your numerator should be a greater number than your denominator so that you have a KeQ greater than 1. So let's just think about it. If you had 4 product molecules and 2 reactant molecules, that number, 4 divided by 2, will give you 2. And so that will give you a number greater than 1, which means that you're favoring your products. Now, if your K is less than 1, that means you're favoring your reactants, and your reactants are more stable. And if we were to do the same thing, if we have our products over reactants, we'll see that the reactant number is increasing and the product is decreasing, which means that it will give us a K that is less than 1. K is never a negative number. It's always just a number greater than 1 or less than 1. So to answer this question, it says, which reaction favors products to the greatest extent at equilibrium? We're going to go with the largest number. So C would be the one that favors products because our KeQ is significantly high. 6.3 times 10 to the 4th power has about 3 zeros. So we know that that's the largest number. And which reaction favors reactants? The only one that has a negative number or number less than 1 is B. So we would go with B. And so when we're talking about Q versus K, K is at equilibrium. Q, we're not sure if our species are at equilibrium. We can do the same thing what we did for K and predict which species is more favorable in that given moment. So if we were to draw a number line and make K be the center, if our Q is greater than K, it means that products are favored. If our Q is less than K, it means that our reactants are favored. And if our Q is equal to K, that means the reaction is at equilibrium. So when the reaction quotient is greater than the equilibrium constant, the reaction proceeds more in which direction? So if your reaction quotient is greater than the equilibrium constant, that means you're favoring products. This is what I need you to think about. If you have more products, that means that we're going to have to shift left. So shifting left would make it a reverse direction in order to reach equilibrium. So when the reaction quotient is less than the equilibrium constant, so if Q is less than K, we're favoring our reactants. And in order for the reaction to reach equilibrium, we have to shift right. So we'll proceed in the forward direction. And when the reaction quotient is equal to the equilibrium constant, the reaction proceeds more in neither direction because it's already at equilibrium. So let's look at this example. We have 2 SO2 gas plus O2 gas that produces 2 SO2. Well, this is at equilibrium, so it's a reversible reaction. The same time that you're making reactants, you're making products. Or Kc is equal to 3,900 at 2,000 K. Very high temperature. Very important information here. Write the equilibrium constant Kc for the reaction. Or Kc is equal to products over reactants. So it will be SO3 raised to the second power over the concentration of SO2 raised to the second power and O2 raised to the first power. I know what you're thinking here. You're probably thinking, why am I not using parentheses and partial pressure? Well, if the question exactly told us to write the Kc, even though the states of matter are gases, we want to write it in terms of concentration so that we'll earn our point on the AP chemistry exam. So I'm just following exactly what the question says, and I'm writing the Kc, which means that I'll put everything in brackets and my exponents will stay the same. So that's my A. For B, a reaction vessel contains 0.15 molar concentration of SO2 and 0.150 molar concentration of O2 and 2.0 molar concentration of SO3. When the reaction reaches equilibrium, will the concentration of SO3 increase, decrease, or stay the same? So since I know what my equilibrium expression is, I need to figure out what my Q is so that I can compare my Q to my equilibrium expression and see which species will be more dominant. All right, so it's the same formula as the Kc. It's the concentration of our products over the concentration of our reactants. And we're just going to substitute in what we have. So the concentration of our product SO2 is SO3 is our product, sorry. SO3 is 2.0 molar concentration. And we're squaring that and dividing it by the concentration of SO2, which is 0.15. And we're squaring that. And the concentration of O2, and we're raising that to the first power. When you do the math, you will get the concentration of your Q value to be equal to, you get a Q value that is equal to 1,185. And then you need to figure out which species is more dominant. Will the reaction shift right, left, or what's going to happen? So we're going to compare our Q to our K. K is in our middle, and K is, according to the question, or equilibrium expression, has a value of 3,900. Now, our Q value is 1,185. So our Q is less than K, which means that the concentration of our reactants will have to decrease so that the reaction could shift right and increase the concentration of our products in order to establish equilibrium. All right, so the concentration, to answer the question specifically though, will the concentration of SO3 increase, decrease, or stay the same? Since we're shifting right, the concentration of SO3 will increase. We're going to look at our Rice tables. Not sure why. Okay, so Rice tables, very fun. I really like to do this stuff. At a given temperature, 0.30 moles of NO, 0.16 moles of CO2, and 0.5 moles of ClNO were placed into a 10-liter container. The following equilibrium is established. At equilibrium, so here's the reaction equation. At equilibrium, we have 0.6 moles of ClNO was present, and it's asking what is the number of moles of CO2 present at equilibrium. And then we're calculating the equilibrium constant Kc. All right, so we're going to annotate moles CO2, moles of ClNO, and 10 liter, that's our volume. The following equilibrium is established. Reactants, products. At equilibrium, this is key. 6 moles of our reactant was present. What is the number of moles of CO2 present at equilibrium? What we want to do is create or rice table. So our reaction equation is 2ClNO and 2NO and Cl2. So what goes into our rice table? Units such as ATM, molar concentration, or moles. In this case, we're experimenting with moles. And initially, we had 0.5 moles of ClNO. And NO, we had 0.3 moles. And Cl2, we had 0.16 moles. Or change, we do not know that yet. But what we do know is that at equilibrium, 0.60 moles of ClNO was present. 0.60 moles of or reactant was present. So then this means that I can deduce what's the change, what's happening here. So if initially I had 0.5, but then I went to 0.6, that was an increase in my concentration, which means that my change will be a positive number. But there's a 2 here, so it becomes a positive 2x. So if my reactant side is increasing, it means that my product side has to decrease, and decrease by the coefficient amount. So minus 2x and minus x, or 1x. So what we can do now is to solve for our x. So if we have 0.500 plus 2x is equal to 0.600 moles, we can solve for x by doing the inverse operation, and we get 0.5 divided by 2 on both sides. X is equal to, I need a calculator. Okay, so this will be 0.1 over 2, which is equal to 0.5 or 0.05, sorry, 0.05 moles. And so if x is equal to 0.05, we could go ahead and substitute in for the question asked for the number of moles of Cl2. So Cl2 initially had 0.16 and minus x, which is 0.05. At equilibrium, the concentration of our Cl2 is 0.11 moles. And that's our answer for A. And we need to calculate the equilibrium constant, Kc. Well, if we need to calculate the equilibrium constant, Kc, and we just figured out that this one here is 0.11 moles, we need to figure out the same thing for the NO. So it will be 0.30 moles minus 2 times 0.05, which is 0.30 minus 2 times 10. Wait, 0.1, sorry. Which is equal to 0.20 moles. I hope I did that right. Hold on, let me get a calculator. I need a calculator. So it would be 2 times 0.05, which is equal to 0.1, and then 0.3 minus 0.1 is equal to 0.2. So 0.2 moles goes here. So now we could go ahead and calculate the equilibrium constant, Kc. So we know that Kc, this is part B, Kc is the concentration of our products over the concentration of our reactants. And it will be NO raised to the second power and Cl2 raised to the first power and ClNO raised to the second power. So if I were to substitute in my values, I would get concentration of NO, which is 0.20 moles squared, concentration of my Cl, which is 0.11 moles raised to the first power, over the concentration of 0.600 moles squared. And when I put that into the calculator, I should get my answer. And whatever that answer is, I'm not going to pause to do the calculation for that, but whatever that answer is, that's the answer for that question. So let's look at Le Chatelier's principle. Le Chatelier says that whenever a system is stressed, the system needs to work to overcome that stress and reestablish equilibrium. So we're given this equilibrium. We're noticing that we have a reactant here and it's at equilibrium and it produces the product, but it's a reversible reaction. We're given the delta H and it's positive. A positive delta H means that the reaction is endothermic. Endothermic means that the reactant's heat is treated as a reactant. So we could add heat on the reactant side. So the question says, in which direction will the equilibrium shift when N2O4 is added? So if we add more N2O4, there's too much N2O4 on the reactant side. We need to shift right in order to reestablish equilibrium. So it will be shift right. Or we could say forward. And if NO2 is removed, it means that we need to put it back. The only way we can put it back is unless we shift right. So shift right. And if the pressure is increased by the addition of N2, well, I'm looking at this equation, I'm not seeing any N2, so I'll say that there will be no impact on the pressure. And if temperature is decreased, which means that we're taking away the heat from the reactant side or taking away some, we need to put it back, which means that this is forcing our products to make more reactants, which will therefore increase our heat, which means that this reaction will shift left. And then the last topic, we're talking about KsP here. And KsP means solubility. Something that's soluble means that it will dissolve in water. So let's look at NaCl. NaCl is a solid. What we do know is that when ionic substances go into solution, they will dissociate into ions. Here is the equilibrium expression for the dissociation of NaCl. Notice that anything that has to do with K, whether it's KeQ, KcKp, or KsP, which is solubility product, we notice that it's still products over reactants. But why is this the KsP without anything at the bottom? Well, the only substance that we have here is an ionic salt, which means that a solid will not go into our KsP equation. So this is the expression. And then similarly to HBr, we'll see that HBr will dissociate into these two ions here. And the KsP is written as a concentration of each product species. And similar to what we have been doing so far, the coefficients become your exponents. What you should be thinking about, though, is that the KsP for NaCl is exactly 36. And the KsP for HgBr2 is 6.26 times 10 to the negative 20. Notice that this is a very small number. Notice that this number is very large. This very large number means that this NaCl, once it goes into water, will completely ionize. You'll see a lot of these products, these ions inside solution. Unlike this value here, the Ksp is very small. This molecule will probably not completely dissociate in solution. And let's look at this last question. It says, consider the slightly soluble salt, PbCl2, with a Ksp value of 1.7 times 10 to the minus 5. Write an equation that shows the dissolution of PbCl2. So we need to write our equation. If PbCl2 is or salt, we know that it's a solid. Once it dissociates, it will dissociate into lead ions, Pb2 plus. So what I did here was I took the 2 and brought it up and made it a positive 2. So it dissociates into Pb2 plus. So it's PbCl2, and 2 chlorine ions, because the law of conservation of mass, there should be the same amounts and types of atoms on the reactant side, and on the product side, the charges must also balance and make sense. So there are 2 chlorine atoms here. I need to account for them on the product side as well. So that is the equation that shows the dissolution. But once it goes in solution, remember they become aqueuses. So I'll just put that as my state of matter. And then the Ksp is therefore Ksp is equal to the concentration of my products over my reactants, but my reactant is a solid and will not go into the equilibrium expression. So that will be lead Cl minus raised to the second power. And then it says, what is the molar solubility of PbCl2? I can go ahead and create a rice table. My reactants, which is PbCl2, and my product, which is Pb2 plus and 2Cl minus. But I could cross this part out because I know that it's a solid and won't have any impact on my Ksp. Initially, though, I'm going to make the concentration of my products 0, because before they went into solution, it would have been PbCl2. So there are no ions initially, but once the reaction starts going, we will have some type of ions being produced. So that change will be a positive X and a positive 2X. So at equilibrium, we could just add these two rows together. We'll get X and 2X. We also know that equilibrium, the Ksp is equal to 1.7 times 10 to the minus 5. So we can go ahead and solve for the molar solubility by substituting what we have into the Ksp expression. So Ksp is equal to the concentration of our lead ions and our Cl minus ions. At equilibrium, our Pb has a value of X right here, and Cl minus is 2X raised to the second power, and our equilibrium constant, or Ksp, sorry, which was given to us in the problem, is 1.7 times 10 to the minus 5. If we're solving for X, we will get 4x cubed on this side is equal to 1.7 times 10 to the minus 5. If we go ahead and solve for X, or X is going to be equal to 0.0162 molar solubility. And this is our final answer.